Hello, everyone. In this video, we'll explore two other applications of projections and orthogonal subspaces and orthogonal projections. The first one is an application to when you want to solve a linear system that is inconsistent, so it has no solution. So what we're going to do in this case is, well, if AX equals B is a system with no solutions, we'll look for the next best thing, which is to find a vector v as close as possible to the vector b, but such that if I take the linear system AX equals v instead, this is consistent. So this has a solution, unlike AX equals B. So how can we do this? Well, the idea is exactly the following. Saying that a linear system is inconsistent is the same as saying that the vector or constants B does not belong to the column space of A. So let's call the column space of A W, and you see that the situation is exactly the following. There's a subspace W, the column space of A, and B does not lie on that space. Every vector in the column space of W makes the linear system consistent, and we want to get the one that is as close as possible to B. In other words, the vector that we're looking for is nothing but the projection onto W of the vector B. More precisely, well, here's what's going to happen. When we try to solve AX equals projection onto W of B, this is consistent because everything in the column space of A makes a consistent linear system. And its solution is the one that satisfies that A times X is as close as possible to the initial B. In other words, V is indeed the closest possible to the initial B. And the reason why we're interested in that is that AX will not be equal to B, but it will be close to it, because AX will be PW of B. And so the distance between AX and B will be the same as the distance between PW of B and B, which is the smallest because of the properties of the projections. Let's try to have a look at an example of this. Here we have a matrix A, 1, 1, 3, 1, 2, 1, and the vector B. You're welcome to check that the linear system associated to these two is inconsistent. So then the way we can apply what we just said is the following. First, you want to compute the projection of B onto W. The projection of B onto W is the usual computation. You pick a matrix C whose columns are a basis for the column space of A. In this case, you can use the matrix A itself. So C and A are the same. Then we have a formula for the projection matrix, which is given by C times C transpose C inverse C transpose. Multiply that to B. I omit all the computations here, but what you should get is 17 over 6, 76 over 15, and 121 over 30. The next step is that of solving the linear system AX equals B. Again, here I omit the details, but you can set up a linear system whose augmented matrix is the vector you found right here, whose last column of the augmented matrix is the vector you found there. Solving this linear system gives you a vector V, 18 over 30 and 67 over 30. This vector is the one that minimizes the distance between AX and B. In this particular case, if you compute the length of this vector, you get, if you compute this distance, AV minus B, then I shouldn't call this B. I'll call it X. it's the vector that minimizes the distance ax minus b. And in this particular case, I've used v above. That's why this is not good. In this particular case, you get that the distance is 1 over the square root of 30. Okay, let's have a look at another application, which is similar in spirit, but slightly different. Now the problem is, I have a linear system, ax equals b. There are some solutions, but I want to find the solution that is the smallest length. So the solution that is the smallest in norm, as the title says. So to do this, let me remind you of a fact about solutions of linear systems. Any solution of the linear system looks like the sum of a particular solution Vp and a homogeneous solution Vh, a solution to the linear system Ax equals 0. In other words, every solution of the linear system is one particular solution plus any vector inside the null space of A, because the null space of A is exactly the set of solutions of Ax equals 0. So the situation looks as follows. I have a subspace, the null space of A, which I call W, and I have one particular solution, this orange vector Vp, which is one special solution of my linear system. So the set of solutions of my linear system is the null space translated exactly by that one particular solution Vp. So this yellow, this orange plane here is the set of solutions of the linear system Ax equals b. Now I've drawn some few other things in this picture. One of them is the perpendicular, the orthogonal complement to the null space, which is this red dotted line, dashed line. And you see that, so the norm of every vector is the distance to the point, the origin. And you can see from this picture that the closest solution to the origin is exactly the vector lying above it, straight above it. To compute that vector v, you can observe that it is exactly given by Vp plus this other vector z, which is a homogeneous solution of the associated linear system. Z is a vector in the null space of A, and Vp plus z gives you exactly V. Okay, so that's the setup. Our goal is to actually compute V. So here's the next observation. The vector z that we need to add to Vp in order to get to our vector V, which is what we're after, is the opposite of the projection of Vp onto the null space. You see that the projection of Vp onto the null space is this arrow pointing to the left. If you flip that arrow, you get exactly the vector z that you're looking for. So the solution with the least norm, one way to find the solution with the least norm, which is our vector v, is to take a particular solution Vp and subtract from it its projection onto the null space of the matrix of the linear system. Let's do this in an example. Here's our linear system. I'll just write it in terms of augmented matrix. When I do the reduced row echelon form of that, I get this matrix here. And then you can write down all the solutions to this linear system. They look like this. They're going to be given by a vector, minus 14, 9, 0, plus the free variable times another vector. And you see here exactly the decomposition I meant before. You have a particular solution, this vector up here, it's Vp, and you have all of these other vectors, x3 times the vector minus 3, 2, 1, those are just elements of the null space of the matrix A. So now what we want to do is to find, among all these possible choices of x, the one with the smallest norm, which will be given by taking the particular vector Vp and projecting it and subtract its projection down to the null space. Okay, so let's do this computation. The null space is one-dimensional. It has a basis given by the vector -3, 2, 1. So I'll take my matrix to be -3, 2, 1, and I'll compute its C transpose C, and then I'll compute C transpose C inverse. Let's start with C transpose C. This is -3, 2, 1 times -3, 2, 1. So when I compute this, I get 9 plus 4 plus 1, it's 14. C transpose C is equal to 14, is a 1-by-1 matrix, so it's a scalar. The inverse is nothing but 1 over 14. So by our formula, this thing in the middle here should be CTC inverse. The projection of the vector VP onto the space, the null space of A, is given by C times CTC inverse times CT VP. Let's write out all of these things. C is the vector -3, 2, 1 times 1 over 14 times, here we have a vector -3, 2, 1 times the vector VP, which is -14, 9, 0, if I remember correctly. Yes, that's what it is. Okay, so we can clean this up a little. -3, 2, 1. Then I multiply the last two vectors here, and I get what? 3 by 14, that's 42, plus 18 plus 1. So I get 51 over 14 times -3, 2, 1. Okay. So our vector x at the end will be the vector v particular, the solution given by that, and we will subtract this projection PW VP. I'll pause the video for a second to make sure that I did all of the computations correctly. Okay, after careful double checking, so this dot product here is a little different. There's a 0 there because it's -3 times -14, that's 42. 2 by 9 is 18, 1 by 0 is 0, and that's a 60. Okay, I like this better, and I think now it's correct. So what we get here is -14, 9, 0, minus 1 over 14 times -180, 120, and 60. Okay, then, yeah, I mean, we can simplify this further, but the theory is all good up until this point. This x, this vector here, is the vector whose norm is the smallest possible among the possible solutions of the linear system that we started with.